could go in either direction, so it doesn't matter where it goes. It's not correlated with the direction of the arrow. And whenever we have this, we put in our formula for the scattering amplitude something that looks like k squared minus m squared plus I epsilon. Okay. Now we will also have another kind of particle. So this is the rho meson. And we will have, again, some momentum k, have k squared minus m squared plus I epsilon. There is an interaction vertex. Now the interaction vertex is something of this form. Okay. And every time we see something like this, you see that we have to have an arrow coming in and one arrow coming out, because when we do the contractions, in the weak contractions, as we did last week or 2 weeks ago for the scalar field, we can only contract this guy with a phi and this guy with a phi bar. So we will only produce either this propagator together with this one or vice versa. So I guess you guys were finishing the other tutorial, right? The statistical mechanics tutorial.
Yeah. Freddy, where did how did we get this?
What?
So,
yes.
In last week we did real scalar field, right?
And in their homework, they did the complex scalar field. So they are all experts in the complex scalar fields. And today in the tutorial, you also did the complex scalar field. Yes.
Can you repeat what you said about the weak contractions?
Yes. So when you have the interaction, so today you showed in the tutorial, right, that when we do the weak contraction with the phi bar and phi bar, we basically get 0. And phi with phi, we get 0, right? Now, when we have this in the correlation functions, right, we will have to do weak contractions, but the weak contractions will only produce propagators which came from phi dagger, okay? So that means that at the vertex, so this vertex will be produced by contracting this guy with some phi coming somewhere else, and this phi with some phi dagger coming from somewhere else. So the phi with the phi dagger will produce a propagator of this form, and the phi dagger with the phi will produce a propagator of this form. Okay? Of course, here we're only looking at the vertex. So we're looking at the final version of the Feynman rules. There are several versions. There is a version for computing correlation functions in coordinate space. There is a version for computing correlation functions in momentum space. And this was the final step, which was the version of Feynman rules for computing scattering amplitudes. Okay? So there is, for every time we see this vertex, we get a minus IG. Okay? Now, from the LSZ formula, we concluded that if you want to compute some scattering amplitude, like the scattering amplitude you were asked to compute today, okay? So what do we have to do with this? Well, we have to start with our correlation function with 4 fields in there, okay? Then go to momentum space, and that correlation function will have in the external leg some propagators. And what do we have to do with those propagators? We have to chop them off, okay? Or the other way we decided to do it was to multiply by the inverse propagators and then take the limit as the momenta was going on shell. And that was our low budget version of computing a multidimensional residue, okay? In the end, we said, well, we get exactly the same kind of Feynman rules that we would get for the scattering amplitude, for the correlation function, except that every time we see an external leg, we don't do anything to it. Okay? So let's try to draw some of the Feynman diagrams that contribute to this, to leading order. Actually, let's draw all the Feynman diagrams that contribute to this, to leading order. So we have nucleons PA and PB coming in, okay? So how can they interact? Can I join? Is there any vertex that allows me to connect these two guys? No, so I cannot connect them. But what can I do? Well, I can try to use this, right? So this guy could go here and give me something that looks like this. So that looks pretty good. And remember, the other rule was that we're only supposed to draw what kind of diagrams? When we compute S-matrix elements, connected diagrams, right? That's why we're drawing connected diagrams only, okay? So which guy can go out here? Well, this one could be the nucleon carrying K1, and this could be the nucleon carrying K2. But who said that this guy had to be K1 and this guy had to be K2? Nobody. Therefore, you could also have K2 and K1 here. Okay? So this is K1 and this is K2. Now, am I missing any diagram? Is there any other possibility? Which one?
But that's not scattering with nucleon anti-nucleon.
Yeah, I think we're done. At least I cannot imagine drawing anything else. Maybe there is something else. If there is, say it now or don't say it until the end of the lecture.
One question concerning crossing symmetry in this case.
I'm not. Let's postpone that discussion, okay?
Cannot we have something which goes like this?
Something that goes, what do you have in mind? So this one, oh, if you want to keep K2 in the same place, then indeed this guy would go like this, and this guy will go like that, and then they will join with that. But it's the same diagram as this. Can you draw it? Draw it on your notebook, okay? And then try to convince yourself that what you're drawing is this guy. I also did it. It was like, there must be this. Oh. And instead of doing that, let me ask you: is this the diagram you're thinking about?
No, I was thinking in the direction of of the lower part going the other way.
No, we don't get to choose these directions, right? Because these are nucleons. So this theory has two kinds of particles, nucleons and anti-nucleons, okay? So we don't get to choose the direction of these arrows. If we had started with anti-nucleons, then the arrow will be different, okay? Very good. So we only get these two diagrams. Let's compute what they are. Okay, so we follow the Feynman rules. We don't do anything with external legs, so that's actually great for these Feynman rules. We have two interaction vertices, so we get minus IG squared, okay? And we get this guy, the propagator. This propagator is the only one that appears, so we get an I over the momentum flowing here. What is the momentum flowing through this line? Well, I'm sure I'm going to get it wrong, so you better start thinking. So this is going to be PA, I think, minus K1. Minus, we use that guy with a mass m squared. Right? Plus, minus IG squared, I over PA minus K2 squared minus m squared plus I epsilon. Okay? Very good. So let's do one more example. Now you can go on and keep going and add order G cube and higher terms, okay, if you want. But we just did the leading order. Let's try something else. Let's try now something like an antinucleon plus a nucleon going into antinucleon plus a nucleon. Okay? So where are the Feynman diagrams this time? Okay, yeah, so for B, we have a line like this. For A, we have a line like this. Okay, for the antinucleon, we have a line like that. We still have the momentum PA going in and the momentum PB going in. Okay, now for the guys coming out, we have K2 and we have K1. Now, remember, these lines are the relics of weak contractions done when we were computing the correlation function, okay? That's why there are arrows in there, okay? Try to remember how we got S-matrix elements from the LSZ reduction procedure from correlation functions. In the correlation functions, these guys were actual objects that we computed from weak contractions, okay? That's why they have an orientation, because they were contractions with phi dagger. Okay? Now, how can we connect the dots here, literally? Well,
they can annihilate it with those.
Yeah, these two guys can come together, and these guys can do this. Now, is there any other option?
The same as those.
The same as what? The same as before. Oh, you mean this one? You mean this one? Excellent. Very good. So we get it, right? And now we compute. We compute minus IG squared I over this momentum. So we get PA plus PB squared minus M squared plus I epsilon. Okay? Plus minus IG squared I over P. So the momentum flowing here would be PB minus K2 squared minus M squared plus I epsilon. Okay? Very good. So we have these two objects. And here is something, one of these quotation mark problems, which is show that they satisfy, yes, you guessed it correct. Crossing symmetry. Now, the catch is that every time you move one guy to the other side, you have to put a bar on it, okay? So you will analytically continue the momentum. So you can pretend that a guy that was outgoing becomes incoming, but in the process, you will also have to flip the kind of particle you have. So something that was a particle outgoing would become an anti-particle incoming, and something that was, well, you know, vice versa, right? Okay.
One question. So
yes.
If I take, for example, the weak contraction for incoming one, and I make a complex conjugation of it, I get the other one, right? Both are related like that. Why we call them particle and anti-particle?
Oh, because they have different charges.
Okay, it's because
that's the only reason. Yeah, they are identical otherwise, and they have different charges. But there is another reason why we call them antiparticles. You should play the lottery maybe today. You're not feeling lucky today? Well, you should, because you're guessing exactly what we're going to do next.
No.
Well, what we're going to do next is actually another computation. We're going to compute what happens when you have a row meson, okay, and goes into nucleon anti-nucleon, okay? Or, yeah, okay? So if we find that this is actually possible, right, you could also think that these guys are being produced as a particle and an antiparticle out of a row meson, okay? So this is another reason why these two objects are called particles and antiparticles, okay? So let's actually compute this. Well, to leading order again. I'll leave it up to you to go crazy and do 10 orders in the coupling. So what are the Feynman diagrams that contribute to this, to leading order? Well, it's very easy, right? We have this guy with some momentum k, say some momentum p. We have this guy going with some momentum k1, and we have this guy with some momentum k2. So there is only one possible Feynman diagram, which is this, okay? And therefore, we get, so that was great, very, very fast computation. So we're done. Now, let's try to interpret this, okay? What does this mean? Well, we could actually put this in a formula that looks like a differential cross-section, okay? Remember, we had this object, square, but what could it mean, okay? Well, last time, if we had two particles incoming here, we dressed this with the d-libs of the outgoing particles, okay? These were the final states. So why not put it in there, too? After all, the final states have not changed. They are the same kind of final states that we had before. Before, we made this something that had nice Lorentz transformations, or at least the correct Lorentz transformations for an area, by putting 2 powers of the energy times the relative velocity of the 2 beams that were coming. Now we don't have 2 beams, we only have this guy. So the only invariant thing that we get to put in here is actually the mass of this guy.
Why do we put it in?
Well, because I want to get something that has inverse units of time. What is the only sensible quantity that we could be computing with this? Well, it's called the decay rate. Well, the decay rate is really the integration, the total integration of this. And this object is equal to 1 over tau, where this is the half-life of rho. Okay? Now, is this always true? Can we always, every time that we have a cubic interaction, we can pretend that this guy decays into two objects? It shouldn't be true, right? Because that doesn't sound quite intuitive. When do you think this process should be allowed? Look at the Lagrangian. When what? No, there is a range of parameters for which this is allowed. Just look at the Lagrangian. Yeah, the masses, right? If the mass of this guy is very small compared to the masses of these guys, this looks like there would be no chance that it could happen. So what in this formula is going to kill the process if the mass of this guy is small compared to the masses of this guy? The d-ellipse, excellent. Yep. Remember that inside here, there is a delta function that tells us that P minus K1 plus K2 has to be 0, right? Otherwise, none of this makes any sense. Okay? Now, if, say, that the mass of the meson is equal to 2 times the mass of the nucleons, what do we find? Well, we can go to a frame where P is just M 0, 0, 0. Sorry. And that would imply that this is satisfied if and only if the nucleons, each one of them, happens to be okay? So that means that the 2 nucleons are produced at rest, okay? If this happens, when our meson decays, the 2 nucleons are produced at rest. If m is greater than 2m, what happens? When our rho decays, the 2 mesons are produced, but they are produced with some kinetic energy, okay? So the mesons, the nucleons, are not at rest.
That is the picture, the rest frame of the primer.
That's right. That's right. So I went to the rest frame. That's what I mean by this. Yes, very good. Now, if m is less than 2m, then nothing happens. Meaning that we get 0. Because the delta function will not have any solutions. Okay?
So, why can't you have them with the enzymes having equal and opposite?
Sorry?
Instead of them both being 0 and the special components ki, why couldn't they be equal and opposite?
Oh, because they must be on shelf, right?
Okay, that's not sure.
These are physical particles.
Did you say where the factor actually comes from?
Where what?
The factor actually comes from? I think so.
Yeah, but that's a long story. It's not very, I mean,
There's a variation.
yeah, it's some normalization, and then in the end, it's exactly the one that you need for this thing to be the inverse of the half-life, which is not a particularly fascinating definition, right? So it's just so that you relate it to something that is standard. Yeah. Okay. That's very good. So our last example, before we switch gears, is actually going to be, let's call it okay, or SED. Good. So what do? Well, we start out with our Lagrangian. Well, as you see from the name, what are the fields that we're going to try to put together? A scalar field and our Maxwell field, right? Well, we know that this is really what we would like to start with. There are problems, we gauge fix, we do everything that we did yesterday, and in the end we come out with the rule that we're basically just going to use what the propagator looks like, not think too much about it, and impose some conditions on the incoming and external possible polarization states. Okay? Let's see how far we can go with that. We will also have a Lagrangian that we will add to this that has scalar fields. Okay? I'm going to start with a complex scalar field, but at some point we should find out why what I'm going to try to do will be impossible with real scalar fields. So try to think about that. So this is exactly the same that we have on the other board. Okay? And now I'm going to try to make these two guys interact somehow. How can I do it? Well, I don't know. So let's just try to build things that are reasonable. Okay? What do I mean by reasonable? Well, let's try to build interactions by putting together objects that make, first of all, Lorentz invariants. Okay? We need the scalars there. And second, our Lagrangians must be real, right? So they better be Hermitian as operators in the end. Okay? So, well, what's one possibility? Of course, we want to put terms, we want to write down terms that contain all three guys, all three objects at the same time, okay? That would be the simplest theory that we can write down. Because if we only had phi and phi dagger together and no a's, that would be a complicated, complex scalar theory, which we could have studied, but we didn't, okay? In fact, you could, if you wanted to, now that I'm thinking about it, you could add, if you want, an interaction of this form. This would be the complex analog of what? Of what theory? Phi form, right? So you could add it if you want. But once again, I'm giving this lecture, so I choose not to add it. Okay, what else? So, as I said, we don't want any interactions that don't involve all three at the same time, all three fields. So, well, I can start with something like this, but if I write this, and I put 1a mu together with this, that satisfies the requirement that all three are together. But what's the problem? It's not Lorentz invariant. How can I fix it? Excellent. I heard two solutions, so we have two possibilities. So one possibility is to put a mu here, okay, with a parameter a, say. And the other possibility that I heard was to say there is a b, and we can make another vector with derivatives. So we can act on either this guy or on this guy.
What about G mu acting on A mu?
Well, by integration by parts, it would be a linear combination of these two, right? Integration by parts. So that term can be written as a linear combination of these two up to a total derivative. You see what I'm saying?
No. If you fly D mu on A mu, you will get back. Okay.
Okay.
What about the node vector?
Yes.
So we consider constants which are scalars. Do we consider constants which are vectors?
Which are what do you mean by vectors?
Like a, like an AB mu, which is more of a background field.
No, so far I'm considering. Well, a background breaks Lorentz invariance, right? I mean, if I say all of a sudden I turn on an electric field in that direction, right? Do I expect the physics to be rotation invariance? No. Okay. Yes. Oh, sorry.
Just, there are no terms with the second derivative of A, like del A, del mu, A mu, del mu, A mu. We don't want any terms like that.
You mean
with
a term?
Two derivatives. I just mean quadratic as derivative of A.
Quadratic in derivatives of A. Something like, oh, you're saying perhaps we could have something like, something like A nu and
Yeah.
then
Yeah. You can contract the mu's or mu's however you.
mu A nu. Yes, but that would be a more complicated theory, more complicated than what I want. Yes, you could start adding more terms, right? Now, here is an exercise for you. If you add more terms like this, compute the dimension of the coupling. Okay? Very good. Go crazy. Just start adding things as crazy as possible, and compute the dimensionality of the couplings, and see what happens.
So, what guide do you have to produce like physical theory? I mean, you can just go to whatever you want. There's so many possibilities.
Well, we're actually going through every single possibility.
But we've not exhausted the possibilities with this.
Yes. Yes, we have.
Which is
Yes.
The second derivative term?
Do your exercise, compute the dimension of the coupling, and realize why I'm not including them.
There's still something
Yes.
to be another constraint that the Lagrangian must be Hermitian.
Excellent. So the last one that I mentioned was that the Lagrangian has to be Hermitian. So this guy has to be real.
Which is
Sorry. Oh, that's a triangular. I mean, this is not an epsilon. It means it belongs. And therefore, this guy has, this C better be B star. Okay. Okay, excellent. So that's as far as we can go with the requirements I impose. Now, we want this thing to actually describe the interaction of particles of helicity plus minus 1, massless particles of helicity plus minus 1 with a scalar field of mass m. Now, the best that we know how to do with Lagrangians is to actually try and describe the particles with massless particles of helicity plus minus 1 with a vector field. Okay? Now, a vector field has too many degrees of freedom, as we discussed yesterday. In general, it has 4 degrees of freedom. Okay? So, the only way, and we know that was the physical reason why we had to preserve, or we had to impose gauge invariance, is that we need 2 of those degrees of freedom to be redundant. So what if we keep B and A completely arbitrary? Okay? This theory will not be gauge invariant, right? What do I mean by gauge invariant here? Well, we have to impose gauge invariance. Because we know that this guy has too many degrees of freedom. So we need a redundancy by this much. So a redundancy here means that our Lagrangian has to be invariant under that rescaling and under that transformation. If we have A, B, and C completely arbitrary, is this invariant? No. In fact, not even if you try to plug this into there and you ask, well, is this ever invariant? You will find that the only solution is A and B equal to 0. That's terrible. So it means that, well, it depends on your point of view. If you want to end the lecture soon, you will be good. But if you really want to think about all possibilities and be serious about all possibilities, according to your principle, we should really go through everything. So we should try harder, okay? So under this transformation, maybe we can enforce that our field phi also transforms, okay?
So is this the only gauge invariance we can demand from our field?
Well, it's the only one we need.
It's the only one we need.
Yes, it's the one that actually tells us that A only has 2 propagating degrees of freedom. So it describes, remember, if we find another way to describe particles of helicity plus minus 1 without ever talking about the gauge field A, is that better or worse than what we're doing? Depends on what?
Your perspective.
Well, from my perspective, the answer would be yes. Okay. But we human beings, so far, only know how to do this using a vector field that has redundancies. Okay. Yes.
Under the gauge transformation, do you want the Lagrangian to be actually invariant or just invariant up to a third derivative?
We want the Lagrangian to actually be invariant.
Why not? Why is just up to a third derivative not enough?
Well, you could impose that too, but I mean, yes, okay, fine. Impose that is up to a total derivative. Doesn't matter. It doesn't change what we're going to do. Yeah.
So, I mean, A doesn't have to go to 0 at infinity, if mu does, right? So if we have a total derivative, it doesn't imply that, that the action would be invariant, because A may not be 0 at infinity, it can be pure gauge, while still F might be 0. So that's why I think we need the Lagrangian to be invariant.
Let's think. Well, you could always say, well, let's impose that whatever variation, we integrate that field to 0, that pure gauge to 0 in the end. You could also say that, right? So there will be some objects that would allow you to.
Well, we'd have to add something to the theory because, for example, we can take an instanton or something, which is not 0 at infinity, and then the total derivative term would not be 0 at infinity.
Right. Yes. Then there is no problem with having a pure gauge at infinity.
Right.
Okay. Yes.
You said that to fix this gauge invariance, you must require that your fields transform in a certain way. Isn't that like putting some extra information by hand into the theory?
No, remember, we're looking for transformations that leave the Lagrangian invariant, right? It's just, okay. Well, that reminds me. So you should know that there is a transformation that leaves this Lagrangian invariant, right? A U1 transformation. So this Lagrangian is invariant under sending phi to, well, that's a silly notation. Okay? So we know that. So this Lagrangian is invariant under this transformation. Okay. So why not try to combine this together with this transformation and see if we can get something out of it. Of course, if this guy is just an overall phase, there is no chance of helping out the problem with this guy. But
can you explain, please, how that condition takes out 2 degrees of freedom?
no, because that was the whole lecture yesterday. You can watch it again. Okay, so we go again and then say, well, we have this guy. Okay, so let's try to use it. So let's use this thing to actually fix the problem we have. Okay, so we said that if phi is a constant, if theta is a constant, then no help. Okay, so we should allow theta to be a function of x. In fact, we should try to coordinate and lock it or relate it to this transformation. Okay, so I'm going to allow theta of x to actually be proportional. So let me actually introduce, so we were in A, B, C. I don't want to use D because D would be a derivative and we'll get all confused. So what's the next one? Yes. Okay, very good. So we have this, pure coincidence.
No.
So exercise. Show that with this, under this assumption, if at the same time that you do this, you send phi to e to the I, EW of x, phi, okay? Then the combined transformation the total Lagrangian, well, the first one is obviously invariant, right? This piece is invariant because it doesn't contain anything else but A. So the piece LA is invariant, no problem. Now this will not be invariant anymore, right? Why is not invariant? Because the derivative will hit our function and will produce more terms, okay? Of course, it cancels out from here, no problem. There is no contribution from here. All the contributions come from here. So we seem to be making life worse because this guy will not be invariant anymore. But things will be great if whatever we get from here cancels what we get from this guy. And that happens, so that's your exercise to show that that happens if we set A to be, yeah. Let me just get the, to be E squared. And if we set B to be minus IE. Okay? So let's go back here and make the replacement. So the theory that makes sense as our scalar electrodynamics would be an E squared A. And we'll put here a minus IE. Here we had B star, so we get a minus sign. Actually, since both things are multiplying the gauge field A mu, we can put them together as a single object. Okay. So this is a theory we're going to consider now. Yes?
Seems that for take any value of E and I'll have different interaction Lagrangian, so why not sum over all the E's that I have?
Sorry, sum over what?
All the E's.
Which E's?
So, I mean, if I have here, E was chosen arbitrary, right? It's an arbitrary.
I mean, all I'm saying is that this, I'm proposing the simplest answers, where this guy is proportional to this guy.
Yeah, but
I'm calling the constant of proportionality E.
however, that's, I mean, the constant of proportionality fixes A and B.
By the constraint that
True.
I have to get something that is invariant. Yes. What's the problem?
No.
Okay. Very good. So let's now use our theory and derive the Feynman rules. After all, every time somebody gives you a Lagrangian now, you should just sit down and get the Feynman rules. Okay? Let's actually derive Feynman rules for scattering amplitudes. For our theory, right? For our scalar electrodynamics. Well, the first one is that yesterday we worked hard to get propagators for our photon field, right? But we have many kinds of photon fields labeled by mu, okay, labeled by an index mu. So we have to tell people who are going to use these rules what the propagator is for different values of the field here and for different values of the field here, okay? So the rule, the propagator that we got yesterday in momentum space, meaning you just remove the integral over d4k and the e to the minus ikx, right? That would be the momentum space version, ended up being something like this. Okay? Which is nothing but saying that when we have a space component, this field of ours behaves just as a regular scalar field, right? And if the indices are different, we don't have any propagation. That's also sensible, okay? That's what we got yesterday. The whole lecture was just to get this one. But we got it in coordinate space. Now in momentum space, this is a formula. Well, we now have the propagator for our complex scalar field. It has some momentum k. It's just I k minus m squared plus I epsilon. Okay? Now comes the tricky part, the interactions. Well, let's start with the first one, right? The first one is over there. So, how do we think about it? Well, it has, whatever it is, it has a nucleon and an anti-nucleon, right? So we're looking at the term coming from E squared A. So allow me to write this as follows. A mu, eta mu nu, okay? I'm writing the same term that we have over there. Phi dagger phi. Okay? Can you see that this is the same as the term that I have over there? The first interaction term. I'm just rewriting it like this. It's a silly thing. It's just that I want to be able to tell what happens when I have different components of the field together with these two guys. Okay? So when I do weak contractions, I want to be able to tell these guys apart. Okay? So we have a nucleon and an anti-nucleon interacting with two of these guys. So the wiggly line is a standard notation for any vector boson, okay? This is a vector particle. Well, not true. Sometimes people denote it as something that goes around and around, as in a spiral, but not for photons. Photons are always denoted like this. So we have two possibilities. We have a mu and a nu, okay? And the interaction vertex is given by then minus I e squared eta mu nu. But I'm missing something here in this interaction vertex. What do you think it is? It's actually a number. Whoever can figure out the number and tell me the reason.
2?
It's a 2. Now you have to tell me the reason. That's right. That's right. There is a symmetry here. Of course, this is only non-zero when these two indices are the same. So there is a symmetry. And that symmetry, we always compensate for it by adding to the Lagrangian a half, right? In lambda phi to the 4th, we had 1 over 4 factorial to compensate for that symmetry. In the mass term of the real scalar, we had mass squared divided by 2. That 2 there was to compensate for the symmetry. In the complex scalar, we don't have the 2 in the mass term. Why is that? Because there is no symmetry. Now, we don't have a choice. We don't have it. We just don't have it there. So the symmetry We cannot account for it in the Lagrangian, so we have to put a 2 here. And that's irrelevant. I mean, that's just a factor of 2.
Why is it negative?
Because the interaction, go back to the last, well, you could ask the same question here.
Well, no, that would.
Oh, sorry. Oh, yes, yeah, okay. Very good. That's right. So in this case, it will be positive. Thanks. Very good. Okay, the last one would be what? Oh, the last one is even trickier. So let's treat the last one together, all together, right? So the last one involves a nucleon, anti-nucleon, and just a single photon. So let's call the momentum of this guy K1, K2. Of course, we know that the momentum flowing here will be K1 plus K2. You would say, but wait, you're doing an interaction vertex. Why do you have to put momentum? We never do that. Well, what's the difference in this case? No, it's actually very different. In this interaction vertex, we didn't have momentum, right? I didn't put momentum because it was, everything was about the vertex, right? Yes, this interaction has derivatives. None of the previous one we had in the course had derivatives. So this is a truly new object for us. Any reason to be scared? Of course not. I mean, we work in momentum space, right? If we work in momentum space, those derivatives are just k's that are there. So they also behave as if they were couplings, okay? But all we have to do is to remember the k's of the particles that are participating in the interaction, okay? It's as if well, it's not as if, the coupling depends on the k of the particles that are interacting, okay? So it's as if we had an infinite number of couplings, one for every possibility of momentum. Okay? So the interaction vertex will depend on that. Okay? So what is it going to be? Well, it's going to be minus IE. Of course, it has to be proportional to that. And then, what do we get? Well, we will get a K coming from the nucleon. But this, the first term, sorry, let's start with the first term. So the first term has a derivative acting on the anti-nucleon, okay? So the first term will give us a factor of K2 mu. This is from the first term. Is that clear? The derivative becomes a factor of K2 mu, because there is a mu, right? From the weak contractions, we're going to get that mu will contract with something else later on. Now, how about for this guy? Well, first of all, we get a minus sign, okay? There is a minus sign in the Lagrangian. Now it's the nucleon, the one that has the derivative. So we have a K1, okay? That's it. So we're done with our Feynman rules. Well, but not quite. Almost done with the Feynman rules.
Could you explain how you're just reading those things off from those around you?
Yes, I'm going to momentum space, right?
Okay.
I'm thinking about each of the external particles that I'm interacting with, right? For each momentum that they have, as if the momentum was another label.
Okay.
Okay? So we happen to have an interaction that depends on the label of that particle. The label is not only if it's a nucleon or an anti-nucleon, or if it has a vector index. It also depends, I'm thinking about a particle with different k's as a different particle.
Okay.
Okay?
Yeah.
So I'm saying that a particle that is coming here with momentum K2 and a particle that is coming with momentum K1, they will interact with a strength that depend on that. Okay? And the strength is coming from, yeah, it was slightly easier to bring down that. So what I'm doing is saying, well, when I put this in interaction Lagrangian, right, in our correlation functions, and we expand the exponential, remember that that's what we do. We expand the exponential. We will start to do weak contractions. Okay? In momentum space, this will become a k.
Yeah.
Okay? So we will contract this guy with a phi, right? Because the only non-zero weak contractions that we have of this guy are with a phi, not with a phi dagger, not with an a.
Yeah.
Right? So that's why this thing will give us a line with a particular direction. And the coupling will depend on the momentum of that object. Okay?
Where do you get the minus IE from? Is that wrong?
This guy here,
Where does it, should it just be E, not minus IE? So is there an extra factor of I that we've missed?
no, sorry, yes, you're right. So there we had a minus g, and then here we should get, oh, no, well, it comes, yeah, sorry, it comes from the, it comes from the k. Yeah, very good. So these parentheses are all, well, parentheses don't matter, but to understand where things come from, the parentheses are important. So we have we have a minus I, and then EI, this thing, and then the derivatives get replaced by I, the derivatives. Okay. Or minus I, the derivatives. So we'll just have to be careful about the sign when we work out the contractions. Okay. Okay. But are we done? Sadly, no. There is still more work to do. The reason is that I haven't told you. Well, in principle, to calculate things like we did here, we're done. Okay? Because these are all the Feynman diagrams we need. So let's look at this example. Okay? Let's do this example in scalar electrodynamics. What do we have to do? Well, we just replace this by this, replace this by this. Now, is there any other diagram in this particular case?
In second order, there's a photon loop.
But that's fourth order. So this is, we're working up to order E squared. Yeah. We can have, so you're saying we can have a loop.
For that process, you can only have a vertical.
Remember, this is E squared. This is E squared, right? And this is only order E. So if you have a loop, like you're thinking, then it would be higher order. Okay? So it seems to me that this is all. No? There is another one? Which one? Two, so you're saying what, two?
Come in and white and two come out.
Oh, but you see, these two arrows are, these two are nucleons, right?
Okay.
So, yes, in this case, we could have it, because it was a nucleon and an anti-nucleon. Look at the arrows here.
Oh, okay.
So we cannot have it. Okay? Very good, so we're done. We just follow the rules and compute this. But why did I say that we were not done with this theory yet? Because we would also like to be able to have as external states photons. And we have no clue how to do that. We're in deep trouble. So how do we put as external states photons here? And that's what we're going to try to figure out.
One question concerning the indices. In each of those vertices, there should be a mu or a nu, but we're contracting those.
Where? In these vertices?
I mean, we have over there, we have an index mu.
Yeah, so the index mu here will be contracted with that index. Okay, maybe let's actually work out this a little bit. The propagator. Let's start with the propagator. The propagator is not just I over k squared, right? It's I minus eta mu nu over k squared. This k squared is the sum of, okay, let's try it. It's PA minus k1 squared minus m squared plus I epsilon. Okay? That's the propagator. But that looks terrible. We have two free indices. Is that terrible? Well, no, it's not that terrible because these vertices also have indices.
So why is there an m?
Oh, sorry. There is no m. This is our photon, right? So what do we do? Well, we have this vertex. It has momentum PA K1, okay? So we use our rule over there. So we get something schematically, we get an E squared with some factors of I coming from that. But what is important is that we're going to contract now this vertex that has an index. It will have some index. It will be contracted with this index, and this guy will be contracted with the other index. So how do we do it? Well, we just put it in there. So let's start with this one. This one has momentum PB. And how about this? So this momentum is going out. And according to our vertex, what am I supposed to put in there?
Plus.
That's right. So we're supposed to put plus K2. And on this side, I'm going to contract the mu index with PA. This is going in, but this guy also has to revert. Okay? So that's the answer coming from this diagram. I'll let you work out all the other factors, okay, of plus minus I coming from the definition of the vertices. But this is important. This was very important to see how the contraction of the indices happen. Okay. Now, don't think about the indices as magic. The indices are just telling you that these are different particles that can propagate from here to here. Okay. You have to sum over all possibilities, and that's what we're about to discuss. Yes.
Did you at any point have to worry about killing the freedom on a photon, or is that already taken care of by this property?
You see. Yesterday we declared that our propagator was this. Okay.
But that already takes care of killing the...
Well, we sure hope so. We're about to discuss exactly that. So what happens? Plus second term. Okay? So what happens when we have an external state, which is a photon? Okay, so far, we don't have technology to actually deal with that situation. So what are we going to do? Well, let's actually go back to our thought experiment where we have something we know. Say, we have a bunch of nucleons coming in. Okay, so these are actually nucleons. And they produce, say, a photon. We have another bunch of nucleons, and say that they produce one nucleon. Okay. These guys come very happily, and they meet here, they interact, and a photon comes out, and another nucleon comes out, and this guy, once again, interacts with some other things, and produces some nucleons coming out, and this guy produces some other nucleons coming out. Okay, so
when you say we don't have the technology to do that, I mean, we did something similar with this row meson that we had before, right? Where I have a row that becomes.
Yeah, but what is the polarization information of the particle? We're almost, we're not there yet, but we're almost there. So from the point of view of this whole thing, this is just a scattering process that we know how to compute, right? That whole thing is something that I could ask you. Of course, you wouldn't want to do it, but I could ask you to compute something like this. A bunch of guys coming in, 6 guys coming in, and 7 guys. Good luck with that. Okay? Now, why do I want to think about this? Well, as last time, when we discussed something like this, remember, what were these guys in our thought experiment? These were the object, the experiment, the part of the experiment that produces the beams, one of the beams going in. With some momentum PA. This was another part of the experiment that produces the other beam. This is the part of our experiment that does what? The detectors. Those were our detectors. So, but from our point of view, this is just an scattering experiment of these guys being incoming and these guys outgoing. Okay? But for this to be a good experiment, we have to tune the momenta of these guys so that what happens? They are on shell, of course, but the sum of their momenta has to be well, yes, of course, it has to be PA, but by momentum conservation. But what do we need PA to be? In order to actually make sure that we're going to have a physical photon product, it has to be a null vector. So it's not obvious. So we have to do lots of things to scatter in order to precisely produce a guy that has the sum of these momenta happen to be the square. It happens to be a null vector. Okay? So we tune our experiment so that PA squared goes to 0. This guy, we have to tune it.
Yes.
So that what happens? We also tune it so that PB squared goes to M squared. Okay? Okay. Now, when that happens, if we think from the point of view of the yellow circle, this is just a scattering process that we know how to compute. Right? We just did one like that. Say with on the top, we only had 2 to 2 mesons. But here we have 6 going to 7. No problem. We can also do it. Now, what would be the only part of the Feynman diagrams that would contribute to this in this limit? What would be the kind of Feynman diagrams that would contribute to this limit if we were computing the yellow amplitude? So let me get the yellow. So, from the point of view of the yellow amplitude, okay, the only diagrams that we would keep in that limit. Oh, and I forgot to say, so what happens to the detectors? We can tune the detectors to only search a range of energies or a range of momenta, so that, guess what? The sum of the momenta of these 4 particles has to be null. And we can tune our detectors so that they only resonate, that they only give us a beep, if the sum of these 3 momentas happen to be close to M squared. Okay? So the only contribution from here, from the Feynman diagrams inside this scattering amplitude, which we know how to compute, the things that will give us a nice contribution will be the ones that have poles there, that blow up there. Oops. No problem? Okay. Okay. Yes?
Does something about the Lorentz invariance make it or prevent us from taking PA squared to 0? like for the same reason that you can't just have a EQED, you can't just have like two electron positron annihilate for a photon, because you go to the further boosted photon.
Well, that's why I didn't put only 2 guys. We can put as many as we want to actually do it.
But
yeah, otherwise you would be saying that it's impossible to produce photons, but look up. Okay, so we have this guy. So the only contribution, say, coming from the photon, that's the part that we don't understand, right? The photon part. How to treat the photon as an external particle. The nucleons are boring. We know already. So from the photon, we will have I. It will be a piece that blows up because it's of this form. And we have minus eta mu nu. Okay? So that's the thing that will blow up. So we have the rest. Okay? We have the rest on the right and this thing on the left, which involves the process for producing this photon. Now, we're going to use a trick. We're going to use the trick that you learned today in the tutorial. Well, maybe it was a misjudgment to actually put it as in the last problem. But if you didn't do it, please try to do it, which was that we can have the completeness relation for the polarization vectors, right, that give us a formula for this as follows. I'm writing exactly what you guys had to prove today. With the same notation. Okay? Very good. Now, remember, our basic assumption yesterday was that every time we have a scattering process in which we have polarization vectors that are not physical, somehow we're going to cross our fingers and say that they vanish. Okay? So these guys were the 2 polarizations that were not physical. Okay? In fact, one of them is proportional to the momentum. Say epsilon plus, I think. Okay, so it's a purely longitudinal polarization vector. So when we plug this here, this contribution, this guy, will combine with this to give us the scattering amplitude where we have a photon, or the probability of producing a photon with a longitudinal momentum. And that is the thing we declare to be 0. So that will not contribute. This guy will combine with this to give us a scattering amplitude where this incoming photon is longitudinal. So we should also declare it to be 0. So the only contribution will come from these guys. Okay? Now, we have these guys. One will go to the left, and one will go to the right. So we interpret this as the wave function of the photons that are being produced on that side, and the photons that are being incoming on this side of the process. Okay? So that's the answer to the question we had. How do we interpret, how do we put in the wave functions in the Feynman rules for our theory? Well, the answer is that we put polarization vectors. Now, we're summing over the 2 physical polarization vectors, the 2 physical degrees of freedom. But when we do an experiment, we usually want to have only one. So what do people do? Well, let's actually finish our experiment. And guess what I'm going to put here? A polarized, yes. So when I put the polarizers, that kills one of these 2 and leaves only one. Okay? So I interpret the epsilon, the polarization vector on this side, as the correct object that I have to use in order to get a scattering amplitude. Okay. So let's finish this part of the lecture, which only took much longer than what I thought.
But
Yes.
why would I need a second polarizer?
Where?
I only need the
Oh, because you have 2 amplitudes, right? There is an amplitude on the left, that is the amplitude that produces your object, and this amplitude, which is the amplitude that takes the object as incoming.
So you can detect only one thing.
So there is a chance that the photon coming out will be of a different polarization.
Yeah, of course. When you do this experiment, there is a non-zero probability of producing one polarization and a non-zero probability of producing the other polarization. Okay.
There's no conservation law at all.
Well, if there is, well, not for the nucleons that we have here. Okay. Okay. So now we can complete our Feynman rules. And the last rule we need is that for an external, let's put it here. Okay. For every time you have an external photon, you have to specify its polarization vector. And what you do is that whenever you see the line of the external photon in question, you multiply by the polarization vector and you contract with the rest of the diagram. Of course, if there is an external photon line, right, the Feynman rules tell you that there is an index left over, and that index will contract with this. Yes?
So that mu index is the index where the line ends?
Yes, so you will have this guy. And as I said, if you have an external line that was a photon line, the Feynman rules will tell you that there is an extra index left over, and that's the index that you have to contract with this guy. Okay? Okay. So let's finish with a little example, just to write the rules. I mean, how to apply the rules. Yes?
Yeah, did we have any freedom in which one we chose as our incoming and outgoing over here? Like,
well, remember in your exercise, what this guy was, the star, is just flips I plus 1 modulo 2.
yeah.
That's why this choice was convenient. Okay? Very good. So let's actually do, the important lesson we're learning here is that every time somebody tells you, I'm going to calculate this scattering amplitude where you have a photon with momentum k. Is that enough information? No. You have to ask the momentum of the photon and the polarization vector of the photon. Yes?
What about if I have no polarizers at all? Shouldn't I trace out the polarization?
If you have what? If you don't have polar, well, then you sum and you trace. Yes,
okay,
that's
so
right. You sum over. You average over the initial states and you sum over the final states. Okay. So if we do something like this, then you just sit down and write down the Feynman diagrams, right? So which Feynman diagram we can write? We can write something like this, where we have this, and now we have our PA going here, PB, K2, K1, okay? And now we have to remember the polarization vectors, okay? So when we write down our answer, we have to remember that this guy comes with his polarization vector. Now, as an exercise for you, write down what these vertices contribute here. Now, the indices will have to be contracted in such a way that they are contracted with this guy. And then at the end, we get some nu. Okay? Is there any other diagram that contributes to this?
is that second one at start?
One not starting.
Yeah, there would be another one that would look funny. Is there another one? Now it's your diagram, right? The one you wanted to say. Because we can have something like this, but now using the quartic vertex. That guy. Right? That's a new diagram that we didn't have before. Is there another one? No? Okay.
Why is that? That's epsilon star. Yeah.
Why is what?
Epsilon mu star.
Because I told you what the polarization vector of the outgoing particle is. If you want to think about this as an incoming particle, you have to put the star. Well, but that's part of another discussion. Okay, very good. So we have like 1 more hour, right?
That's enough time to describe.
Nobody got the joke. Okay, no. But let's actually give a preview of what we're going to do tomorrow. Okay, so we get preview.
You see the video?
No, very good. So we saw in the previous case of the nucleon that I can have the anti-nucleon producing or tapping root of those. Here, there's nothing like anti-photon, right?
Yep.
But if I want to check here crossing symmetry, I have to conjugate my polarization vector.
Yeah, the photon, it's its own antiparticle. Okay, just like the real scalar.
Okay.
What happens to the
Oh, if you want, oh, yeah, then you have to, yes. So you have to be careful because a photon with a polarization in a given direction, when you think about it as inverting its momentum, you also have to flip the polarization. You have to conjugate the polarization. Yes?
So when we did the grid convex vertices before, right, you have the photon and it has lower indices, and then you have the triple vertex.
Yeah, all indices are contracted with the Minkowski metric. Okay?
Well, just like when you have the triple vertex, you have upper indices, and those get contracted with the photon vertices.
Yes.
But here you have lower indices. So how
Okay, now we have upper indices. Okay, so a preview of what we're going to do tomorrow. So tomorrow we're going to switch gears completely. And we're going to say, well, following, no, actually not, it's very good. So actually following Sad's point of view, we have to exhaust every possibility that there is in the world. Okay? So we did complex scalars, we did real scalars. By the way, you should try to think why our little trick here would not work for a real scalar. And so we have to keep going. But how do we keep going? Well, we have to think about the Lorentz group and the representations of the Lorentz group. Okay? And the trick we're going to use, okay, is something that we did in QFT0. In QFT0, you represented the Lorentz group, where you found a way to think about the Lorentz group as SL2C. Of course, this guy happened to be, actually, this guy was a double cover of SO3, 1, meaning that there are two elements here that come from the same element here. Okay? In other words, say the identity, okay, here can be mapped into what? Or vice versa. Say, which elements of SL2C map to the identity under the map we study in QFT0? Exactly, plus minus the identity. That's why it's called a double cover. Okay? So let me remind you, but I want you to go through what we did and you did in the tutorial in QFT0. Okay? Let me remind you how we made the connection. We started with a vector. Okay? And what did we do with that vector? we said, well, let me define, actually with the index down, a 4-vector made out of Pauli matrices. The 3 Pauli matrices that you know and love, plus the other 2x2 matrix that you should love even more, which is the identity. Okay? So these 4 guys make a 4-vector, and we constructed a 2x2 matrix that we call boldface B. Okay? Then we said that the determinant of this object, or you guys computed it, I think. What was the answer?
The normal vector.
Exactly. Was this thing. Now V, if B is real, what happens to our matrix? Yes, it's Hermitian. Okay. So if we want any transformations applied to our matrix, we want to have a transformation that preserves the property that the new object is Hermitian. So we're going to have something like this. Okay? But we want a transformation that preserves the determinant of B. So under this transformation, the determinant of B goes into the determinant of V times the absolute value of the determinant of my matrix A. So to preserve the norm, or to preserve the determinant, we need, so to preserve we need that the determinant of A is equal to 1. Well, that means that the determinant of A is a pure phase.
Freddy, that's a squared and that's a plus.
Yes, thank you. No.
Shouldn't that be plus minus 1 then?
No.
No, it's the absolute value.
Because A is
Okay, absolute value would be 1.
Yes. So the determinant of A can be a phase, okay? But any phase that I have on A that produces its determinant can be removed by multiplying A by a matrix that is a pure phase. The identity times a pure phase. But the identity times a pure phase doesn't affect V at all. So it's not something that acts on my matrix B. Okay? So changing A by a matrix that looks like e to the I theta, okay, and A like this, does nothing to V. So it's not part, or it's completely irrelevant as the information that we're looking for as the group that acts on V and preserves the norm. So we can use this to set the determinant of A to be always 1, okay? And then the group of 2x2 complex matrices of unit determinant is called SL2C. It has how many complex parameters? Complex parameters. 3. So the complex dimension of SL2C is 3. But we want to compare it, or we want to think about this guy as being homeomorphic to the Lorentz group, which is a real group. So we should really think about the real dimension. We should think about the parameters that will allow us to explore this group as complex numbers with real and imaginary part, and think about them as independent objects. So we want to think about the real dimension of SL2C, and that happens to be 6, of course. Okay? For every complex number, we have 2 real parameters. which matches the dimension of the Lorentz group. Okay? Now, what I want you to review is the little calculation you did, which constructed the homomorphism between the two. So what I want you to do is to remember the following. That rotations in SO 3,1 could be generated by taking this object as a generator and then taking A. So this will be a rotation around some particular axis, okay? An angle theta is generated by the following object. Okay? I believe you did it, right? So you expanded this exponential, and you found that you get an alternating sum with some factors, and the sum can be resummed each of the components, and you get cosine theta, sine theta, depending on the pieces that you chose, okay? And there are boosts, and the boost will be given by. So in principle, as a complex algebra, these are all the generators. If you allow these guys to be complex, the objects that you multiply by. But since we're thinking about this as a group with real parameters, so we have to separate them, which is good, because the Lorentz group also has a natural separation in terms of rotations and boosts. And this guy will correspond to the imaginary part, or the imaginary part of these three elements. Okay? And for a given boost, you have, now this is a notation I want to use. And here in this case, we have the same thing, phi dot chi. Okay? Very good. Let's see, is there anything else that I want you to review? Well, just let me tell you that this is called the fundamental representation of SL to C. Okay. It's a representation because it allows you to study the group as being represented as 2 by 2 matrices. Yes?
So phi is a non-compact text value.
Well, phi, oh, you're complaining because phi looks like an angle.
Yeah, I'm just reminding
Yeah, so, so phi is something that parameterizes boosts. And we know, of course, that boosts are non-compact, right? So you can take a boost as much as you want. So, any candidates for the notation of something that is not compact?
R.
R? Yeah, but R is a radius. It's not compact, but it's also. Little b, but it must be a vector. Oh, no, okay, yeah, little b. That might be a good.
Doesn't look nice.
It doesn't look nice, yes, I agree. But that's fine. So B doesn't look like an angle, which is all what we want, right? Okay, very good. So, by the way, this means that is this representation unitary? Yes, no, yes, no.
No, you cannot have unitary representations of the Lorentz group in a finite dimensional, but this is a translation.
That sounds good, but why is that so?
Why is that so? Because you can keep doing it and come back to the same point. Like in the space.
Yes, but that's what is called a tautology, right? You said that would be the definition of something that is compact. You say, well, I cannot have unitary representations which are finite dimensional because it's not compact. So anyone, does anybody know the answer? So the question is, this representation we found is not unitary, right? So then the question is, why could there be any unitary representations which are finite dimensional? This is a two-dimensional representation because it represents a group as operators or matrices that act on a two-dimensional space, okay? So the question is, could you have maybe a 10-dimensional representation which is unitary? This one, we failed to construct one that was unitary, right? These ones are not unitary. These ones are. Why are these ones unitary? Well, this is okay. We could do it because the rotations form a subgroup, but the rotation group is compact. But still, that doesn't explain anything. It's another tautology, right? We're using the answer to explain the question. Yes. Well, let's try to think by. Yes, let's try to prove it by assuming that it's true, right? Imagine there was one, I don't know, 100-dimensional representation, which is unitary, right? Very good. If it's unitary, right, it means that these guys are unitary matrices, 100 by 100, no matter, or whatever number you like, 1 million by 1 million. That means that they are elements of the set of all possible unitary matrices. But that group is a group of unitary matrices, right? And the group of unitary matrices is known to be compact, okay? And the reason it's compact is precisely because the group of unitary matrices precisely has this property, right? That in any direction that you go, you always come back to itself because you can pick up a direction and it will always have the structure of a little u1, okay, which is compact. Now, if we find that this is true, if we find this 100 million dimensional representation, it would mean that our group, SL2C, could be thought of as a subgroup of the unitary group, which is known to be compact. But that would be a contradiction, right? Because our group is not compact. So it cannot be a subgroup of something that is compact. Okay. So we can end here.